This program is part of the Better Boating Series, dedicated to safe, fun, and informed boating.
Yeah, it was quite a trip today down.
Beautiful trip, beautiful weather.
Seas were not too bad.
Should have been sailing.
Yeah. Well, listen, us power boaters, and you know.
Well, I got drawn into it.
Oh, hi, how are you? I'm Lenny Bendel, and I'm skipper of the Wild Turkey 101, and this is Skip Archibald, who's skipper of the Northerly, a sailing vessel, if I remember correctly, is the way to say it?
That is correct.
Okay, well, we get into our arguments, of course, from time to time about the differences between power and sailing, but one thing we agree on, and that is the reason that we own boats is to take them away from the slip, right?
Take them away from the slip to take me away from the slip.
I know what you mean.
Yeah.
One of the things that is the most important thing that you can learn, actually, in owning your boat is being able to get from one place to another safely, and that's the subject that we're dealing with today. We're calling it modern coastal piloting, and the reason because it's modern coastal piloting is because we're going to include the use of electronic aids such as LORAN and radar to confirm our position and fixes that we take, right?
Well, Lenny, you're the high-tech man with all the modern equipment, but I'm the traditionalist in this
business. Is that
business,
what sailboaters are, traditionalists?
Yeah, but anyway, we'll put our talents together and see what we can do today.
Okay, very good. Pardon me, I think that one of the things that we need to start right off with is coastal piloting is the art of being able to get from point A to point B, your destination, to do it safely. And to accomplish that, you have to have the basics. The basics are the tools. And we've set out an array here of things that are required for safe coastal piloting. Skip, you're going to start, if you would, on my far right, your far right. And let's go down and just briefly explain what we have on the table and what their uses are.
Okay, well, we're not going to talk about everything that's available, but we are going to talk about the essential ingredients. First, there are parallel rules for coastal navigation, and we'll talk about these a little later on. In the coastal navigation kit, there is the triangular compass. There is the course plotter, which has a compass inscribed in the central part of it and has a scale. And then there is a one-armed protractor, which will be used for navigating. We'll demonstrate a little later on. In addition to all these tools, there's the dividers, and the dividers are indispensable, used for establishing distance, and we'll show you some other techniques. In addition to that, you ought to have a few other tools of the trade. One of them that I consider for coastal piloting is absolutely essential is the hand-bearing compass, a device you hold in your hand and you take a sight, and in taking that sight it helps you establish your various fixed points. And there are several kinds of those. We have two here. One is, this is the open type, and it has a little button on it so that if you're not sailing at night you can depress it and it'll light up your compass. The other one is very similar. You simply look through it, sight your object, and you release a button, and it locks the compass card that's on the inside here, and you can take your reading from there. There are other kinds of things that we need to have as well. Lenny, I think you have a pair of binoculars in front of you there.
Yes, I do. Binoculars are extremely important because when you're sighting your fixes and you're looking for an object to take a fix from, quite often they're in the distance and you can see them on the horizon and not see them too clearly. So a pair of binoculars is very, very important. It's also important for seeing other vessels in your way. Most important, of course, is your chart. Here we're running a chart from Anclote Keys in Florida to Crystal River, Florida. And that's the cruise that we're going to be taking today from Crystal River to Tarpon Springs, the famous Greek community. Things that go along with the chart, though. This is something that you should have. This is called Chart Number 1. Chart Number 1 is put out by the United States government. It is a publication of the government. And this is what explains all of the symbols and the abbreviations in all of the charts that the government publishes for marine use.
We need to note, Lenny, that the symbols found on charts are so numerous and so diverse, there's no way in a brief period of time we have to explain all of them, although we will touch on some of the more essential
Absolutely.
ones.
We'll touch on some things like color differentials and how to identify landmarks and that type of thing. But as Skip says, there are just hundreds and hundreds of different kinds of uses of a chart, and for us to spend the time to go over it with you is not very practical at this point. Let's talk also about this particular publication. This is called the dates of latest editions. This particular publication serves one of the best purposes I can tell you about, and that is to find out the chart that you have, if it is the latest chart for that particular, or the latest edition for that particular chart. As an example, the chart that we're dealing in now, its latest edition is 1984, and here we are in 1987. So we don't want you to think if you went out to buy a chart that was dated 1984 that it might be an old chart. It may be the latest one available. Other things are, these are catalogs that NOAA puts out, which is, of course, the National Oceanographic and Atmospheric Administration. And these are the catalogs of the charts that they have available. The Pacific Coast, the Atlantic and Gulf Coast. They also have the topographical charts, bathysphere charts, and so forth. These charts are all available to you. The catalogs are available. What you have to do is first learn what you need for your own area, and of course what you're going to use if you're going from one point to another. There are private charts that are put out, charts, companies like ChartKit, okay, and there are 2 or 3 different versions by other companies, similar, small, compact charts. Price-wise, you just have to check the area for yourself, but in many cases you will find that the packaged charts in, let's call it ChartKit form, okay, are no more expensive than buying all of the individual charts, and then sometimes might be less expensive for you than buying individual charts for each area of coverage that you might be interested in.
And for the coastal piloting enthusiast, who tends to be the person who's out for the weekend and so forth, they're usually easier to stow. I just find them to be very, very practical.
Oh, I agree with you. We use them all the time. There's one other thing that we have on the table, and that is not something that is normal for basic coastal piloting, but this is a sextant, and as Skip had indicated before, Davis does put out what they call a charting kit, which is all of the material that you saw over here, except for the compass, the hand-bearing compass, but they also put out what's called a navigation kit, which includes a beginning sextant. So that is something else that you could be looking at if you were really interested in getting into heavy navigation.
They also include in there a nifty little thing they call their TSD, or time, speed, and distance computer. It's just a little tool for computing your time, speed, or distance while traveling.
You know, that's one of the things that we're going to be talking about in our videotape today, and that is, it is most important that you be able to determine how long it's going to take you to get somewhere, how long it's taken you to get from one point to the other, how fast you're traveling, and how far you're going to travel. Time, speed, and distance is basic mathematics, but unless you have a thorough understanding of how to use it in the courses that we're going to be going through, it will not do you well to not understand time, speed, and distance.
Absolutely, and when you get into such things as calculating drift and wind currents and so forth, you have to have an essential grasp of that, and we're going to cover those kinds of things.
There's one tool that we need we haven't mentioned yet, though. We haven't mentioned the fact that to do time, speed, and distance, you need a watch with a sweep second hand or a digital readout for seconds.
Very good.
Okay?
Yes.
All right.
We always overlook the obvious.
That's right. Okay, but it's very necessary that you have that. So from that point on, tell you what we're going to do. We're going to set back here and redo our table, and we'll be back with you in just a minute, and we're going to start right at the beginning, okay? We'll be right back.
Let's recap the tools that you need for basic piloting. Of course, you need the parallel ruler so that you can measure your course and get your actual headings. You need a triangle. You also need a course plotter, and be sure it's one that's got a compass in the center. Don't forget the one-arm protractor. That will allow you to rotate the arm around various course lines. Pair of dividers. That'll give you your measurements for distance. The hand-bearing compass to take your fixes with. Pair of binoculars so that you can sight for your fixes, and we recommend a 7 by 35 as the maximum size. Don't forget your charts. Don't forget chart number 1 either. That's what's going to teach you all about the symbols and abbreviations on a chart. Remember the dates of latest editions so that you're sure you're working with the latest one available. Also, don't forget your watch. We need to have one that's either got a second sweep hand or one that's digital readout in seconds. Very, very important tool. One more time, let me recap what we need. A parallel ruler, triangle, course plotter, one-arm protractor, dividers, hand-bearing compass, binoculars, chart, chart number 1, the dates of the latest editions, and your watch.
First thing that you do when you're going to work with a chart to determine where you're going to go and how you're going to get there is to make sure that the chart that you're working with is the latest edition chart that's published. Now again, we do that simply by taking a look at the date of latest editions. We look in the lower right hand corner, if you would, Skip, just indicate that, and that tells you the chart number, and it also gives you the date of that chart's printing. This particular chart is number 11409, and we look that up here, and it says September the 29th, 1984 is the last one issued. By the way, just as a point, be sure that you look at the date of the book of latest editions. Be sure you've got the latest one of those. This particular chart is supposed to be 1984 September, and that's exactly what it is. Now, as we proceed down the chart, it'll also show us that the soundings or depth readings on this chart are registered in feet. So when you look at the depth, be sure to remember that that is registered at mean low tide. If you have a depth indicator that is indicating in fathoms, which some of the older units do, then you can convert easily, because at the bottom of the chart is a conversion table which will convert feet to fathoms or to meters or vice versa. Now, as we continue to move down the chart, it reiterates what the name of the chart is. This particular one is Ann Claude Key to Crystal River in Florida. And moving further to the end, it tells you that this is a Loran C overprinted chart. Now, what that means is that the topographic people, the people who made the map, they made the map first based on the shoreline, depth indications, and so forth, then added to that the Loran lines for plotting position. And those Loran lines on each chart, you will have different line numbers depending on the area that you're working in. The Florida area is working on what they call grid 7980, so all of the lines indicated here are from the master and slave stations for that grid. Now, as we move down the chart itself, we get into different colors, and I'm going to let Skip pick it up at that point.
Okay, let's, if you'll note back over here in the bottom right-hand corner, we still have part of the legend, and you need to be sure that you read all of the notes and cautions that are contained around the perimeter of the charts. These tell you a lot of information about channels, depths, tide changes, and tell you often the dates at which time these particular readings were taken. If we start here, you'll see these lines, these definite change in contrast, represent the coastline. So everything to your right of this represents land. You'll notice that the first part of the coastline is green, and in Florida that's because much of our low-lying coastline is swamp, marshland, and so forth, very close to sea level.
You know, that's a good point, though. Let me just, if I can, bring this out for just a second, because we've been talking about the use of chart number 1, and what better indication than this. The very first thing, which is page 1, shows you the coastlines and how to read them, and you'll notice there's all different combinations of sand, rock, tree lines, marsh, swamp. All of the things that Skip was showing you here, you would see in much greater detail on chart number 1.
And you need to be sure and know that, because there are all kinds of symbols that tell you about the texture of the land and so forth. You'll find that land is generally colored towards yellow. Once in a while you'll find a chart that shows land is gray. Now as we move out to sea, you'll see that we have a darker water area here, and the darker the area means the shallower the water. And in Florida, at the Gulf side of the state, waters drop off very, very gradually, something like about a foot per mile. So the first lines of demarcation that you see along on the chart here represent shallows, up to around 4 or 5 feet. And if you look at all of these numbers, and you'll remember that our soundings on this chart are in feet, you'll see that these represent the shallows. As you move out to past the next series of lines here, and the coloring becomes a little lighter, the range in depth here is from around 6 feet out here to around 16 or 17 feet. And then you have another line of demarcation running through on the chart, and beyond it the depth goes from that 16, 17, 18 foot on down and out to the edge of the chart where it's about 60 feet. Another thing we need to take a look at on this chart are the lines that are superimposed on it, Lenny.
Yes, Skip, let's talk about longitude and latitude lines. They are the method by which we can find our position anywhere on the Earth's surface. The Earth is divided into longitude and latitude lines. Now, latitude lines runs east and west, and they run all around the Earth's surface. All latitude lines are equal distance apart. On the chart, a latitude line looks like this. Longitude lines run north and south, and because they come together at the poles, they are not equal distance apart. Where a longitude and latitude line cross, it is called a coordinate. If you are also at that point, it is called your line of position. Looking at this example, the equator is 0 degrees, with each pole being 90 degrees away. So there is a total of 180 degrees from the North Pole to the South Pole. Each degree is equivalent to 60 nautical miles. Therefore, 180 degrees is equivalent to approximately 10,800 nautical miles in distance from pole to pole. Each degree contains 60 increments called minutes, and each minute is equal to 1 nautical mile. In each minute is 60 more smaller increments, and they're called seconds. Usually, charts show seconds by tenths. Each tenth of a minute is equivalent to 6 seconds, or approximately 607 feet. On the chart, latitude lines are generally shown as 10 nautical miles apart. As you can see here, there are 10 increments of 1 minute each. Here you can see a minute divided into its tenths. Remember that longitude lines are not equal distance apart, so they're not accurate for measuring distance. The 0 degree longitude line is called the prime meridian, and it travels from the poles right through Greenwich, England. The 0 degree latitude line is called the equator. So everything north of the equator will be called north latitude, and everything south will be called south latitude. Looking again at the prime meridian, or the 0 degree longitude line, we see that everything to the left of the 0 degree line is west longitude, and everything to the right of the 0 degree line is east longitude. Now let's see if we can locate a position on the chart. Using the following coordinates, 28 degrees 20 minutes north latitude and 82 degrees 50 minutes west longitude, let's see where that puts us. As you can see by following the lines, you can locate your position easily. Remember, the heavy darkened lines that are printed on the chart only appear at certain intervals. To find coordinates that are in between the printed lines, simply use your pencil and a straight edge to draw in the lines.
Lenny, it seems to me that from that we establish our location here on the chart. Maybe one of the things we need to know how to do is to figure out our distance from various points.
Okay.
Let's remember when we were talking about the legend, we said one of the things contained in the legend were various symbols for establishing particular kinds of information, and one of them is this nautical mile scale. And I'm going to take the dividers here, and I'm going to set these for 2 nautical miles. You'll see the scale here. I've put one portion of the divider on 0 and the other on the 2.
Okay.
Now There's another way also we could establish this. You remember we said that latitude lines were equal distance apart, and therefore the scale on the side of the map could be useful. And so let's take this 2 nautical miles that I put on the divider, and let's just check that out and see if it works.
Very good.
Let's start at 28 degrees here.
All right, if we're accurate, we should be down to 28.18.
That's correct. So let's see how does that look.
That's
Does that look
exactly where we
right?
are. That's exactly
All right,
where we
so
are.
now we've established that these dividers are set for 2 nautical miles. And let's take that earlier coordinate position we had, and let's just run out and see about how far offshore that position is. 2, 4, and I'll close the dividers. We know we're 4 miles. I'll put this on the 1 and come in here, and it looks to me like we're about 5 4/10 miles
Correct.
offshore. Is that about
That's
right?
exactly right.
So we've got a real easy way to determine distance
Right.
on the chart.
You did something kind of neat too, and that is, of course, the way you use these, as Skip just showed you, is this is a round knurled point at the top of these, and that's simply so that when you set a point, you can twist without having to lose your position.
And the point's sharp, so that it'll penetrate the chart surface and it won't slide around on you.
Skip, now that we've discussed how to find where we are on the chart and how to read the chart basically on the primary legends, the one thing we need to discuss now is how to use the compass rose, right?
That's it. And if you'll notice on the chart, there is a circular pattern inscribed on it with a lot of numbers around it. In fact, there are 2 circles, one inside the other. They're concentric. The outside circle represented the degrees of the compass, and you'll notice the star at the top and the 0. That would be the true north symbol.
All right.
On a compass. So we would know that on this particular chart, this direction is northward, and that's consistent, you know, with what we were talking about, a longitude and latitude lines. We know in our longitude lines run north to south.
All charts, by the way, do have a compass rose to give you the indication of direction.
And then you'll notice on the inside circle, there are a series of numbers, and they don't quite line up. The 0 for north on it is not quite the same as the 0 for north on the outside. And the reason for this is to show the variation due to magnetic interference on the Earth's surface. Because as we all know, the North Pole is not exactly where magnetic north is. It attracts your compass.
In fact, they're about 200 and some odd miles apart, aren't they?
That's right, around 280 some miles. And in where we are in Florida, we don't have a great deal of what we call variation as a result of that. In fact, it's only 1 degree and 30 minutes in a westerly direction as of 1984. You'll notice also on this chart, there's some wording here that says annual increase, and over here 9 minutes. So what you have is an annual change in this variation of 9 minutes, and a little later on we'll talk about that as we get into other aspects of navigation.
Okay, well then, if I am following it correctly, what we have is on the east coast, the Atlantic seaboard, basically, we're almost on the line where true north and magnetic north are very, very close to each other.
That's right.
In a direct line.
That's right.
However, as we moved westward, say out to California, where their variation could be considerably more, that's because of their distance further from true north.
That's right. In fact, by the time we get out to the west coast, we're going to find variations that are in excess of 14, 15 degrees.
All right, so it becomes significant, doesn't it?
It is critical in piloting.
Okay, we'll be teaching you some terms as we go down the line, but little acronyms for easy to remember, like east is least and west is best and that type of thing. Understanding the compass rose is the most important thing that you can do, because when you start working with a chart and you learn that you have to do everything consistently, you will be working with either true north, magnetic north, and compass north. And we're going to get into those very shortly to explain what the differences are between all of them.
That's right.
Okay?
The other thing we need to do, Lenny, before we begin the trip today is talk about some of the symbols on the chart.
Okay.
One of the things we're going to do is take some fixes as we begin our dead reckoning portion of our navigation.
All right, what's a fix?
All right, a fix is where I'm going to stand on the boat with a hand-bearing compass, and I'm going to try and get the best possible reading of the direction of the particular landmark from our position. And I'm going to record the time, and I'm going to record the degrees off of our bow that particular item is located. And I'll try and take another object about the same time and take a reading of it, and we'll record it as well, and through triangulation we'll locate our position on the chart. Let's pick out an object here and just show them on the chart the kind of symbol that they ought to know about, Lenny.
All right, well, let's start right here with St. Martin's Light.
All right. On the chart, we have here symbols. In this instance, it's like the shape of a little teardrop, and with a dot. And then there's some writing or inscription to identify it for us. In this instance, it says St. Martin's, and then there's a series of symbols: an FL, and then a capital R, and then a 4S, then 16 with the foot symbol, and then a number 10 that's located in quotation marks. And let's go over what this really means. We have St. Martin's, that's a point. Then we have FL, which means flash. And if you'd use your chart number 1, you would find that those symbols are all defined in there.
Absolutely.
You have an R, capital R, that means that this flash is red. And then you have a 4 and an S, and that means every 4 seconds this light is going to be flashing red, that it's located on a pole or a piling that's at least 16 feet high at the high mean water mark,
right,
and that it has a number affixed on it, and that'll be the number 10. And so you could use that for sighting the mark during the daytime. You have the red flash 4 in order to identify the mark at night.
Interesting point that we just mentioned, that Skip mentioned, is that we're now using 2 opposing watermarks. All of your depth indication, if you remember, was at mean low water, but all of your height indications are at mean high water. Therefore, if you're at a high tide and it's telling you it's 16 feet above, it is 16 feet above the high tide.
That's right.
The average high tide.
Let's take another landmark that we'll use.
Okay, let's use, say, a tank over
All
here.
right.
Can this be a water tank?
All right, you'll see here that there's a symbol on the shore. It's a circle with a dot in the center, and then there's a descriptor, and it says tank. So we know we've got some sort of a tank located on the shore, and we'll begin looking for that as we're doing our cruising today. Once we find this, I will take a fix or a reading on this, and we'll put down the time, and we'll put the heading. Hopefully we'll identify this particular landmark. We'll identify the St. Martin's Light, and we'll probably find yet a third one. And in using those 3 readings, we'll locate where we are at that particular point in time. We have to be able to identify on our charts the channel marks and our range marks. Channel marks, and I guess we can use as a good example coming into the Anclo anchorage, we come in on a channel mark, which is a red 4-second flasher, 16 feet high. And you know the old rules of red, right, return.
Right.
So we're going to keep that red mark on our right coming in. We'll head from that channel mark to yet another one, and here you'll see a red 2. And the reason we know it's a red is because it's a triangle. And a mark that is a triangular, red, even numbered, will be a red mark, and so we'll keep it to our right or to our starboard. As we turn into the channel, we'll begin to see a series of red marks. We'll also see some green marks, and the green marks will be square and they'll be odd numbered, and we'll know that we keep them to our port side going in. Another interesting thing going into the Anclo channel and into Tarpon Springs, that there are a series of what we call range markers. Mm-hmm. And these range markers are in sets of 2. You'll see that they're rectangular in shape, red with a white stripe on them, and the one that is furthest away from you will be elevated slightly higher than the one that is closest to you. And when you have these 2 lined up with each other, you know that you're in dead center of the channel coming in.
All right, so basically what you want to do then is you want to, like you say, line them up, and when one is higher than the other, the back one is higher than the front one, that's when you're dead center.
And they're lined up.
And they're lined up,
That's
right.
it.
Okay.
The only caution now is you don't want to run straight up to your range marks, because range marks tend to be set out of the channel. They're simply there for you to line up on
So they're
while you're
sight
running
indicators,
the channel.
they're not channels.
That's right.
All right.
And if you take a chart and you can use your rows along with your parallel rules, as we'll demonstrate later on, you can establish the compass heading between the range marks, and that gives you an opportunity to check and see how accurate your compass is on that particular course heading. We're going to take our parallel rules here and show how we can establish the direction we need to run from marker 4 going into Anclo anchorage to marker 2 in the main ship channel.
And this will give us our actual compass heading that we should be taking.
This will give you your compass heading for that particular run.
Okay.
So I've taken the parallel rules and I've placed them on the 2 points, point we're going to arrive at, the point we want to go to. I'm going to walk the rules across the chart, and you notice they're designed so you can do that. One word of caution though, be sure you hold the rules down firmly on the chart so that they don't wobble on you.
The angle
as you're
doesn't
walking.
change.
That's
right,
right, because if it changes, your course is going to be wrong. And I'll walk it all the way across here to the rose. And you'll notice in the center of the rose is an X, which marks a crossing point, the center point of the rose. And you remember that the outside series of numbers were for true north, and we want to adjust for variation, magnetic north. So we're going to use the inside series of numbers. And you'll notice that due south is 180 degrees, and it's going to be just slightly more than that. In fact, it reads to be about 187 degrees. So we would, if we draw a line between this point and this point, above the line we would put a C for course, and we would write in 186 degrees, so or 187 degrees, so you'd know your heading.
187 degrees M for magnetic.
And we know that adjustment's been
Absolutely.
made. Okay.
Okay, so that's how you use a compass rose and parallel rules. Let's review again the important points for reading a chart. The first thing that we want to do is check the date of the chart. Check it with your dates of latest editions to be sure that you have the latest edition. Be sure you read the legend that tells you the measurement for depth, such as feet, fathoms, or meters. Check all the notes, legends, and cautions. Remember that each chart color has a specific meaning. Chart number 1 is your codes for all the abbreviations on the chart. Latitude lines run east to west and are equal distance apart. Longitude lines run north and south, and they come together at the poles. They are not equal distance apart as they get closer to the poles. When figuring distances on a chart, use the latitude lines only, as they do maintain equal distance. Remember that each degree is broken down into 60 minutes, and each minute contains 60 seconds, just like a clock. Each chart has a scale so that you can use either the scale or the lines of latitude for measuring distance. Greenwich, England is the 0 longitude line. Everything west of Greenwich is west longitude. Alternatively, everything east will be east longitude. The equator is the dividing line for latitudes. Everything north would be north latitude, and everything south would be south latitude. The compass rose is always printed on the chart. The outer ring shows true north, and the inner ring shows magnetic north. The difference is variation. Variation is the difference between true north and magnetic north due to interference from the Earth's surface. Understanding and reading of all the charts is of primary importance to good and safe coastwise piloting. Davis Instruments puts out some quick references. One is called the Quick Reference for Coastwise Piloting, and the other is a Quick Reference Navigation Rules. The compass is the most important tool on your vessel, especially when you're coastal piloting. One of the things that we're dealing with in a compass is what we call deviation. Deviation is a mechanical problem. That is not affected by the Earth's magnetic surface. It is affected by other magnetic items. I'll give you an example. This is simply a magnet, but take a look at what happens when it even comes close to the compass. You'll notice that the compass card is just spinning. Now, the closer it gets, the faster it spins. Now, that's a magnet, but what happens with other items that are not non-magnetic? Just a screwdriver. Take a look. Now that screwdriver has just thrown this particular compass off about 30 degrees. So always remember, have your compass boxed, which means have it set up so that all the deviation that is normal in your boat, that's the effects of your steering wheel, any radios that are near, any magnetic surfaces like speakers. And by the way, radio speakers are magnets. Don't forget that. A boxing of the compass simply means that an adjustment is made to get the compass as in line back to magnetic north as is possible, and what they can't get in line, they give you an adjustment card to remember. It's called a steering card.
Lenny, two things have come out now that seem really important. One is that if you have, you decide to try and check your compass out, just because it's accurate on one heading doesn't necessarily mean it'll be accurate on another heading.
That's absolutely right. The reciprocal is not necessarily accurate.
Okay, the other thing, real curious, now this is a Ritchie compass, and it has a metal case around it, and not only that, but has a cap for it as well to keep dangerous sunlight off of it when you're not using it and so forth. Why doesn't that throw the compass off?
Well, it's stainless. It's a non-magnetic material. And that's, again, the deviation that when we look for anything that you're going to need to mount around where the compass is, try and be sure it's stainless or other non-magnetic material. Remember, screws will throw off the compass if they are magnetic. Okay?
So a critical thing is anytime you're going to mount something near your compass, get it up there close to it and make sure that you don't have any interference at all.
Right. And the other thing is, once a year, get your compass boxed, because you're going to change things on your boat like we all do, and something's going to affect your compass reading. So have it boxed for safety purposes once a year. And don't forget, cover your compass, because as Skip says, the compass cards will fade out if they're left in direct sunlight for any length of time. Okay? Now that we know that there are natural and man-made influences that affect our compass, we need to recognize that following a course line based simply on true north will probably not put us where we want to be. We need to compensate our course so that we really do track the course that we want to travel. Let's remember that the factors that affect our compass are variation, which is the difference between true north and magnetic north caused by magnetic interference from the Earth's surface, and deviation, which is magnetic interference caused by items on board your vessel. To figure your compensated course is simple. All you have to do is add or subtract the information that we've already determined from your true course to get to your compass course, and then reverse the formula to go from your compass course back to a true course. There is a simple formula, and it's called TVM-DC. T equals true course, V is for your variation, M is magnetic course, D for deviation, and C for your compass course. Now, the way the actual formula works from true course to compass course is the following. T, or true course, plus or minus your variation, depending on whether it's east or west, equals your magnetic course. Plus or minus your deviation, again depending whether it's east or west, equals your compass course. Now, this is also called uncorrecting. A quick way to remember this formula is true Virgos make dull company. When we want to correct from the compass course to the true course, we simply start at the bottom of the formula and go up, or CDM VT. A quick way to remember that formula is, can dead men vote twice? When we go from true course to compass course, how do we know when to add or subtract? Well, that's easy. West variation is added, and east variation is subtracted. Now that also applies for your deviation. If your deviation is west, you add it, and if your deviation is east, you subtract it. East is least, and west is best. When correcting to the true course, you reverse or add east and subtract west. It's simple, isn't it? Let me show you some examples of how that works. If we draw a true course line of 175 degrees, and we have 4 degrees west variation and 3 degrees east deviation, what is our compass course? Well, we put the 175 degrees next to the T, because that is our true course line. We know that we have 4 degrees west variation, so we're going to put that next to the V and we're going to add it because it's west. Now, that means that when we add it to our true course, we come up with 179 degrees, which is our magnetic course. Now, that's corrected for the difference in the Earth's surface, but we haven't yet corrected for the boat's interference. Now, we have a 3-degree east variation, and east means that we subtracted, east is least, and that brings us to our compass course, which is 176 degrees. See how simple it is? Here's another one. If our true course is 350 degrees, and we have 17 degrees west variation and 6 degrees west deviation, again, what is our compass course? We put the 350 degrees next to our T. We have 17 degrees west variation, so again, we added, it's west. That means that our course now is magnetic at 7 degrees. We also now add our 6 degrees west deviation, and now our compass course is 13 degrees. And as you know, that means that to steer 350 degrees true, we actually have to steer 13 degrees on our compass. Now let's reverse and let's go from our compass course to true course. If we have a compass course of 11 degrees, with 5 degrees east deviation and 12 degrees west variation, what is our true course? Starting at the bottom of the formula, we have 11 degrees for our compass course. With 5 degrees east deviation, we add east now. We now have a magnetic course of 16 degrees. Remember, we also had 12 degrees west variation. We have to now subtract west, and that leaves us with our true course, which is 4 degrees. One final example, going from the compass course to true course, is if we have an 8-degree compass course with 3 degrees west deviation and 5 degrees west variation. Again, we enter our 8 degrees at the C for compass course. We now put the 3 degrees on our deviation line, and remember, it's westerly, so we subtract it. That leaves us with a magnetic course of 5 degrees. We also have a 5-degree west variation, so we put that next to our V, and we subtract that. That leaves us with our true course of 0 degrees. Dead reckoning, or deduced reckoning, is the tracking of your boat's position on the chart using courses steered and your speed through the water. A bearing is the direction of an object from its observer. It may be stated in degrees in true or magnetic values. A fix is one or more bearings plotted on a chart to determine your position. Now let's go on to Skip for some time, speed, and distance work.
You recall a little earlier I said we would come back and talk about speed, time, and distance. And we've created a little formula for you to help you calculate speed, distance, and time. In the formula, S equals speed, T equals time, and D equals distance. Before we get into that though, let's remember one thing with regard to time. Normally you're recording time in terms of hours and minutes. You need to convert your time to minutes. So there are 60 minutes in an hour, so if our time in an example is 1 hour and 30 minutes, that will translate to 90 minutes. So remember that in inserting the value of T in the formula. And the formula is really quite simple. Look at the speed. S equals 60 multiplied times your distance divided by time. Distance is speed times time, remember converted to minutes, divided by 60. And time equals 60 times your distance divided by S. Remember now, you may be dealing with decimal points in your distances, and be sure that you will make the necessary decimal point placement in doing your mathematics. Now to a few illustrations of how we use the formula. Let's begin with speed, where speed is the unknown, and we are aware of what our distance is and what our time is. We take our formula, 60 times our distance, and we've said 4 miles, nautical miles, divided by an hour and a half, we converted to 90 minutes, equals 240 divided by 90. So we have speed, 2.6 knots, a slow sailboat at best. Now let's take a look at distance. Now we've established in the previous formula what our speed factor was, so let's use that one. So we have speed, 2.6 knots times 90. Remember, that's our hour and a half converted to 90 minutes, divided by 60, the constant in our formula, equals 234 divided by 60, means our distance is 3.9 nautical miles. Now let's look at the time formula. We used our constant 60 times 4. 4 nautical miles was our distance that we used in our original formula when we calculated speed, divided by 2.6, which is the speed. That gives us 240 divided by 2.6. And again, our trusty calculator tells us it's 92.3. Now remember, that's minutes, and we'll need to take that and round it off, and you'll see that we have 1 hour and 30 minutes.
Leaving Crystal River, we'll depart marker 1A on a course of 256 degrees magnetic for a distance of 7.8 nautical miles. We will be traveling at a speed of 14 knots. Therefore, using our TSD formula of T equals 60 times D divided by speed, we find that it should take 34 minutes to arrive at our waypoint. A waypoint is a place on our chart which is between our boat and our destination. Now in this case, it's the point where we'll turn southbound. We'll use several other waypoints during our trip. Looking at our chart's Loran lines, we'll have determined that our first waypoint is located at Loran line 14387.5 and 45269.0. We've entered those numbers in our Loran so that it will tell us our course to steer in true degrees, which we will compensate to our magnetic course. Remember that your Loran doesn't take into account drift and set when giving you a steering course. However, by using the cross-track function of the Loran, you can always know where you are, especially to the right or left of your dead reckon course line. Loran always knows where your destination waypoint is and where you are at that moment. It's constantly updating its information to give you the direct steering course to your waypoint. Now, as your vessel is moved off of your course line by drift and set, the Loran keeps adjusting its steering course to keep you on your intended track. By keeping the cross-track error function at 0, you should be dead on your track. Remember, the higher the numbers showing in the cross-track function, the more off course you are. Now, I make it a practice to note my lines of position every 20 minutes or so that I can keep an eye on my actual track. It's also very helpful to know your last TDs or latitude and longitude and the time that it was taken. That's in case of emergency. As sailboats are slower than powerboats, hourly position checks will suffice. Before we start taking different kinds of fixes, let's define more clearly 2 terms: a course and dead reckoning. A course is the direction that a vessel is to be steered. It is also a direction that is being steered. Courses are plotted on a chart by drawing a line from your departure point to your destination, via all the waypoints that you have selected along the way. Course lines are indicated as either true course, magnetic course, or compass course, depending on which reference you choose. Above the course line, you write the letter C for course, followed by the direction in degrees, and followed by T, M, or C for the reference that you're using. Under the course line, you indicate the vessel speed. Dead reckoning is used to estimate your position when you lose sight of all your navigation aids. It is a plot of courses steered and the distances traveled through the water from a known position. By using the time-speed-distance equations we have previously discussed, we can reckon our position. Dead reckoning does not take into account the effects of wind and current. By use of a current diagram, you can adjust for the drift and set in the traditional way, or use the modern method of taking a Loran fix to determine your drift and set from your dead reckoning track. Dead reckoning track should be indicated by the letters DR above the track line. The labeling is then completed by indicating C for course, followed by the direction in degrees, and that is followed by the reference for the direction, such as true, magnetic, or compass course, T, M, or C. Traditional coastal piloting has determined that there are a number of ways to find our position, including fixes with 2 or more bearings and single object bearings. Let's take a 2-bearing fix as our first one. That will be our first on this journey to Anne-Claude Key. Having checked our chart in advance, we know we'll be sighting on 2 different objects. In this case, the power plant at Crystal River and the water tank over in Ozello. The ideal situation is to take your bearings on objects that are 90 degrees apart, but that's not always possible, so get as close to it as you can. The next point is to realize is that when you're using your handheld compass, you can't compensate for deviation. That's because you move around the boat too much and there's too many influences on the compass. So take all of your readings in magnetic. One final point before we take the 2-bearing fix. When taking our bearings, we know where the object we're sighting on is on the chart, but we don't know where we are on the chart. So let's draw in the bearings in its reciprocal form. In other words, what the bearing from the object to your boat would be. If the magnetic bearing to an object is 90 degrees, then draw your line from the object towards you at 270 degrees. By adding 180 degrees to any magnetic bearing that's less than 180 degrees, and by subtracting 180 degrees from any bearing that's more than 180 degrees, you will know the reciprocal. It simply allows you to draw your bearing line from a known position to your unknown position. When you have drawn 2 bearing lines in that fashion and they cross, you have a fix. Your position is at the point where they cross. Let's take our fix. Remember, we are working with the inside compass rose, which is adjusted for variation, so all bearings will remain magnetic. Skip sights the first object, which is the power plant, and he determines that the bearing to that plant is 063 degrees magnetic. The time of the bearing is also noted, and both pieces of information are written down. The second bearing is taken on the water tank, and it's determined to be at 105 degrees magnetic. Again, the time is noted and the information is written down. Now let's move over to the chart. The first step is to locate our compass rose. We're going to add 180 degrees to our first bearing, so we get to the reciprocal, which is 243 degrees. We place our parallel rule on 243 degrees, and we walk it over to the power plant. Now we draw our line. Let's write our magnetic bearing above the line, and the time of our taking the bearing below the line. By the way, we'll always write our times in military time. That's based on the 24-hour clock. In other words, 12 o'clock noon is 12 o'clock, but after that you add 1 hour each time, meaning 1 o'clock would be 1300, 2 o'clock 1400, etc. We repeat this process for our second bearing. Our bearing was 105 degrees magnetic. Again, by adding 180 degrees, we have a reciprocal bearing of 285 degrees. Let's locate 285 degrees on our compass rose and walk our ruler to the water tower. Again, we draw our line from the tower towards our position. We note our magnetic bearing above the line and our time of bearing below the line. Where the 2 lines cross, that's our position. We indicate this as a fix by placing a triangle at the point where the lines cross, and we note the time of the fix on the chart. We now need to put this information in a frame of reference so that we can determine our position in Loran LOPs, or time differentials. In this case, our fix indicates we should be at 14,387.5 and 45,269.0. Let's take a look at the Loran and see what it says is really our position. The Loran confirms our position by indicating our present LOP is exactly where our traditional manual fix indicates we should be. How can we use our radar to confirm our position? Well, let's see what our distance is to our bearing objects from our present position. The power plant, according to our dividers, is approximately 5 nautical miles. The water tank in Ozello is about the same. By placing our radar on the 8-mile range and by moving our range marker out to the 5-mile position, we can see that both our objects are the specified distance from us. Another way is to include the use of the bearing marker and take actual bearings which are relative to the bow of your boat. Now these bearings you'll have to adjust to your magnetic bearing in the following way. Oh, by the way, we'll also draw in our radar bearings as dotted lines on the chart, and we'll indicate them with the letters RB. Then we'll put in the degrees of the bearing, and we'll indicate an M after that for magnetic. Our first radar bearing is to the power plant. It is approximately 160 degrees from the bow. By adding 160 degrees to our magnetic course of 256 degrees, and then subtracting 360 degrees when we go over 360, we can determine that our magnetic bearing to our object is 56 degrees. That's pretty close to our handheld bearing, which was 63 degrees. Using the same procedure, we'll take our radar bearings on the water tower. Now, it's also relative to the bow, and this time it was at 215 degrees. By adding 215 degrees together with our magnetic course of 256 degrees, we find that our radar magnetic bearing is 111 degrees. Again, this is close to our handheld bearing, which was 105 degrees. Now that we've confirmed our position by the traditional and modern electronic means, let me show you some other ways to take bearings. These will be single object bearings. There are several ways to take single object bearings. They're not as accurate as two object bearings, but they can give you your approximate position. The various types of single object bearings are bow and beam bearing, the running fix, doubling the angle on the bow, two bearings and run between, and two relative bearings. Some of the important factors to remember in this type of observation is that distances should be measured over the bottom, and your DR track should be compensated for the effects of drift and set. Also, keep your speed and course constant during the complete observation process. The bow and beam bearing. The object of this observation is to use one object to sight on by taking two different bearings. These bearings are taken at different times. By knowing the time between the bearings and being able to calculate the distance run, we can figure our position. We accomplish a bow and beam bearing by shooting two different angles to the same object. The first one is when the object bears 45 degrees from the bow. Note the bearing and the time. The second is when the object is 90 degrees from the bow. Again, note the bearing and the time. From the information written on the chart, we can determine our time interval. We can calculate our distance using the formula S times T divided by 60 equals D for distance. With this information, we can create a triangle using our course line, that's our DR line, as one of the legs. The basis of this bearing is that the distance covered between the bearings is the same as the distance from the sighted object to your boat at the time of the second sighting. That's the 90-degree one. Let's try it. Using the Homosassa marker, our first bearing is 135 degrees magnetic, taken at 0930 in the morning. Our second bearing is 90 degrees and was taken at 0945. Now we know that our interval between the bearings is 15 minutes, and our speed over the bottom, according to our Loran, is 14 knots. Using our formula, of s times t divided by 60, which is for distance, or 14 times 15 equals 210, divided by 60, that equals 3.5 nautical miles. We can now see our position. As we have an LOP, or line of position, which is the beam bearing, and we know the distance traveled, we have a position that is fixed. Remember, you can also use your radar system to take the bearings, utilizing the techniques that we learned previously. The object of a running fix is to use your first bearing line as the second line of position in the taking of a fix when a second object isn't available. First, take a reciprocal bearing on an object, drawing in the line and noting the magnetic bearing and the time. Second, run the same course and speed for 1 hour. Then move your previous line of position forward, the distance you've traveled. In our case, it's 14 nautical miles because that was our speed. Draw in the line as a dotted line and mark it Advanced LOP, with the original bearing time and the second bearing time below the line. Now sight on a new object, taking the reciprocal bearing. Draw in that line, where the actual bearing that you've just taken and the Advanced LOP cross is your approximate position. Doubling the angle on the bow. This method deals with the same basic geometric principle as the bow and beam bearings. That is, that the distance to the object sighted on the second sighting is the same as the distance run between the sightings. Here's an example. If you take a bearing that is 20 degrees off your bow and you note the time, then wait to take your second bearing on that same object till the angle is 40 degrees or double off of your bow. And if your run time between the bearings was 20 minutes and you were traveling, let's say, at 10 knots, then you would have covered 3 1/3 nautical miles. Remember your TSD formula. 3 1/3 nautical miles would be the distance between the bearings, as well as the distance to the object at the time of the second sighting. Another method for a single object bearing is 2 bearings and run between. Very simply, you take a bearing on an object, noting the bearing and the time, then wait till the angle to the same object has changed by more than 30 degrees. Then repeat the bearing. After plotting both bearings and computing your distance run from the time interval, open your dividers to the distance run. Then place the points on the only place where the points touch each bearing line at the same time. This gives you the boat's approximate position at the time of each bearing. One of the primary problems when you're operating a boat is what do you do when you have a boat that comes at you head on, or one that's going to come across your bow, what we call a crossing situation, or when you're going to overtake. Well, that's what we want to discuss right now. Let's show you the correct procedure for passing, crossing, and overtaking. In Rules of the Road, we discuss 3 different kinds of passing situations. They are the meeting, the crossing, and the overtaking. Depending on where you are determines what rules you're subject to, either the inland or unified rules or the international rules. A meeting situation is where 2 power-driven vessels meet head-on. Neither vessel has the right of way, and both must alter course to starboard if necessary for a safe clearance. Here are the signals. In the crossing situation, 2 vessels have to be not meeting head-on, and they must be forward of 22.5 degrees abaft the beam. When 2 power vessels are crossing and they have the risk of collision, the vessel that has the other on her starboard side must keep clear. Here are the signals. In the overtaking situation, one vessel coming up on another from astern of a direction that is 22.5 degrees abaft the beam of the other vessel, and whose speed is greater so that the distance is closing and is overtaking a slower vessel. Any vessel overtaking another must keep out of the way of the burdened vessel. That's the one being overtaken. Once you are overtaking another vessel, no change in bearing will make you into a crossing vessel. You must keep clear of the burdened vessel. Here are the signals.
Well, here we are, Skip, back in beautiful Kings Bay at Crystal River. We've had quite a trip today and yesterday down to Tarpon Springs and back. What do you think?
Gorgeous weather, and not only that, Lenny, but I think we demonstrated some really fine coastal navigation techniques today.
Sure did. We dealt in traditional piloting techniques. We worked with our radar. We worked with the Loran. And most of all, we've learned how to put them together and use one to confirm the other. Leads us to the next kind of stage in navigation, doesn't it?
Yeah, in fact, I think the next go-round we'll start doing some celestial navigation and use some more sophisticated techniques.
All right, that's something you're going to have to teach me. I don't know anything about celestial navigation.
We'll work on that one together.
Okay, very good. We hope you've enjoyed it with us. We sure enjoyed bringing some of these techniques to you. I'll tell you, now what you got to do is go out and do them. Take your boat, go out and enjoy some trips. We'll see you next time. Bye-bye. We'll see you. Now that you've learned modern coastal piloting techniques, you've also learned how critical it is to use instruments that provide the highest degree of accuracy. Since 1850, E.S. Ritchie has been one of the world's leading manufacturers of magnetic marine compasses. Today, boat owners can select a high-quality Ritchie compass that is a perfect match for their boating needs, power or sail, runabouts to offshore racing, day sailor or maxi sailor. Ritchie even has a selection guide to help you make the choice, and over 60 models to choose from. Ritchie also offers the Ritchie Board portable chart table and the hand-bearing compass to make plotting easier. Ritchie products are available from quality marine dealers and mail-order catalogs worldwide. For more information and Ritchie's latest catalog, contact Burton Sherman, president of E.S. Ritchie & Sons Incorporated, Oak Street, Pembroke, Massachusetts, 02539.